Better late than never. Here we go. Sarah, I have a handout for you, but you'll get it eventually. All right, so I guess this handout, I need to go grab it because there's a lie on there. There's a total lie. It's because I'm stealing these notes from before. Chapter 1, no. Maybe this one, yeah. Okay. Oops. Ding, ding, ding. Where's the lie? Oh. And maybe I'll do this. This is a lie. I'll do it in red. We are just going to talk about it, like I said. So we will discuss the geometric and some other distributions on Wednesday. So we've talked about the normal distribution, and you've got a normal distribution assignment and that you're working away on, I think. And so the normal distribution is kind of our core distribution, whereas another distribution that we have is the binomial distribution. So a normal distribution we use for numerical data, and a binomial distribution is one of the more common distributions that we use for categorical data. Okay, so we have studied the normal distribution, which is for numerical data. And now we're going to look at the binomial distribution, which is for categorical data. And now we consider the binomial distribution, which is for categorical data. Specifically, categorical data with only two outcomes. And I think we've talked about it before, where you can have many categories, but then if there's one category that you're interested in, then it was, yes, you're in that category. And then all the other ones would be coded as no, they're not in that category. So here, a lot of these categorical variables, even if they're not success failure, initially, we can make them be success failures. And so here is for categorical data, specifically, variables with only two possible outcomes. Variables with only two possible outcomes. I'll say even if we have multiple categories, right, I'll just make a note of that. We can lump them as either success, failure. Even if we have multiple categories, we can, oh, that looks bad, worse than usual. We can create a binomial variable. We can create a binomial variable. So for example, if you want to talk about grades, right, you can have A, B, C. I mean, I think there's B minus and B plus. I don't know. There's like a long list, blah, 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 blah. And maybe let's say A plus, A minus, oh, -1, A minus. I did them in a different order. I think you understand them. What if this is the only category that we're interested in? What if an A plus is the only one that I want to predict who is going to get an A plus in this course, right? That's a category. And if you didn't get an A plus, then that's in a 0 category. So usually we denote these as 0, 1s. And so here, this would be the category of interest, which is coded as a 1. And then here, these are all the not A plus, which we can code as a 0, right? It doesn't matter how close you were, right? Even if you're just looking at A's or whatever, right? Typically, that thing that we're interested in is a rare outcome. So things that we might be interested in are, did someone die from a disease? Yes or no, right? And so even though we call them success failures, usually a success is bad, right? That's the thing that we want to try to kind of get a handle on, right? It doesn't have to be bad. In this case, an A plus is really good, right? But if we flip it and we say, okay, I'm interested in who's going to fail this course, right? Then the people who fail would be, well, hard in this class, but in general, right? The people who fail would be coded as a success, right? Because that's who I'm interested in. That's the group that I'm interested in, right? Kind of modeling their behavior. So we have this kind of success failure situation, and I've got it on the handout to save you some writing here. And I don't know why I keep, well, I know why I keep using these, because I've typed them out once and I'm reluctant to go back. But in that tree that's on the side, there's actually an error there. There's some overlap, but first let's talk about this. So a binomial situation is when we have 2 possible outcomes. So that's going to be your first kind of check-in point, because the hard part with solving these problems is you're going to have to read a question and decide, okay, is this a z-score question or is this a binomial question, right? And so how we figure that out is, well, we don't have a mean and we don't have a standard deviation, which are things that we would need for a normal distribution, right? Instead, now for a binomial question, we need to have 2 possible outcomes and only 2 possible outcomes, right? And we have to have some, each outcome must have some fixed probability, right? Which means that those probabilities are independent, right? Flipping a coin, right? It's either heads or it's tails with equal probabilities. There's only 2 possible outcomes and there's some fixed probability, and that doesn't change, right? So we've talked about dependent events already, but now we have to have independent events. Okay. So what we're going to do is, let's say I flip a coin, right? And I say, I'm going to flip this coin 2 times, right? Then what would the tree diagram look like, right? If I wanted to know, so for example, flip a coin 2 times. right? Draw the tree diagram. So then I'm going to have flip number 1 here. Right? And it's either heads or it's tails with equal probability, let's assume. And then I flip another time, which means I get heads or tails with the same probability. We usually want to find stuff like what's the probability of at least one heads, right? So at least one head, so the probability of at least one head is going to be, and we're not going to calculate it because we're kind of moving on to other things, but just to illustrate how complex it can become so quickly, right? So at least one heads I get if I have heads, if I have heads, tails, if I have a tail and then a head, right? So all those three would be, and I'm going to just be sloppy and say the probability of head, plus the probability of head, tail, plus the probability of tail, heads. Or if we prefer, right, 1 minus the probability of tail, tail. But, so what we say is that we're looking for n trials. So in this example here with 2 flips, right, then I have 2 trials. So here in this scenario, n equals 2 trials. I think of it as the number of times that I try to get ahead, right, is going to be, or try to get any outcome really, is going to be a trial, right? And so then in n trials, we're going to see k successes. Right? And so the number of successes, right, here I have head, head, here I have head, tail, tail, head, tail, tail. And so here I have 2 successes. Here I have 1 success. If a success is heads, let a success equal heads, then the probability that k equals 0, and I'm going to start with 0 because that's the one that people often forget, is going to be the probability of tail, tail. Right? What if I'm interested in 1 success? So exactly 1 success. There's 2 ways that that can happen, right? Either I flip a head and then a tail, or a tail and then a head, which means that this probability is going to be the probability of head, tail, plus the probability of tail, head. And then the probability that k equals 2 is the probability of head, head. We can find these probabilities, right, just from the tree. And with only 2 trials, it's very easy to wrap your head around and just kind of map it out and see it. What if you flip a coin 10 times? Uh-oh, right? Because now you're going to have a branch, a branch, a branch, a branch. It just gets out of control, right? And you can't possibly sit there all day and try to figure out how many streams have exactly 1 head and how many streams have exactly 2 heads, how many exactly have 3, up to 10, right? And so that's going to get out of control. And so that's where the binomial distribution comes in, because it helps you just calculate it using formulas instead. So that's kind of cool. So I've got
like the binomial has exactly 2 branches.
That's right.
But the number of trails can be.
That's right. So there's only 2 outcomes for each trial, but you can have as many trials as you want, but there's only 2 possible outcomes in each trial.
At first, when you hit n is equal to 3, I was like, sorry, n is equal to 2.
Yeah. So in this example, n is equal to 2, but now we're going to kind of bump it out to any number of trials. So that's why we use the shorthand n, is we can have any number of trials. And let me see if, oh yeah, my shooting hoops example. Let's see here. So just to illustrate it, how this works, I'm just going to steal this whole thing. And I see on my handout, I ditched that tree diagram. I think I photocopied an old version because I realized that has a typo, but I'll show you how to fix it. Okay. So my example is that I'm shooting hoops. Now, I don't play any sports, and so I know that the probability of each shot going in is 0.2, probably less than that for me personally, but let's just assume, right? And so first off, I'm going to ask myself, okay, what are the possible outcomes and how many possible outcomes are there? If I shoot, let's say it's basketball, I shoot, it either goes in or it doesn't, right? So I have 2 possible outcomes. And then if I shoot 3 times, right? So I try 3 times to get it in, so I have 3 trials, right? What's the probability of exactly 1 shot going in? Yeah. So S is going to be a success, right? So the shot goes in. And so here, what we can do is we can solve this problem in 2 ways. First, I'm going to solve it using a tree diagram, and then I'm going to show you the binomial distribution and how it's doing the exact same thing without the tree anymore for larger number of trials. Okay, just to kind of hammer it home. Okay, so I'm going to draw out this tree. I've got a page break here, so I just want to make sure I have enough space. So I'm doing 3 trials. So here, it either goes in, so an S, or it doesn't. I guess, are you okay if I do a prime?
Yeah.
It's the complement, but it's a lazy complement. It's not the derivative. Yeah. And so it goes in with a probability of 0.2, and it doesn't go in then with a probability of 0.8. Right? So that's my first shot. Then I take my second shot, and you want to make sure that you give yourself enough space, and you'll see where there's a typo because there's 2 overlapping, right? So here there's S and not S, S and not S, 0.2, 0.8, right? These probabilities stay the same. We're assuming I don't learn any skills in this short amount of time. Okay. Refuse to learn from my mistakes. There. Oh. So these, I realized later, when I typeset it, there's actually 2 overlapping, but LaTeX didn't want to help me out there. So it was like, what? They're there, just on top of each other. So there. So then same thing here. I have a shot and a shot. 0.2, 0.8, 0.2, 0.8, 0.2, 0.8. 0.2, 0.8. Okay. Luckily, we're only interested in exactly what's the probability of exactly one shot going in. Okay, so imagine even if you had to deal with this and say, okay, what's the probability of more than one shot going in, including one, right? That's 1, 2, or 3, right? Less than 2 shots, 0 or 1. You have to remember the 0 option because that's the one that people forget. I forget too. Okay, so exactly 1 happens, well, if the first one goes in, then the remainder can't go in because otherwise I don't have exactly 1. So that one's kind of easy enough, right? If the first one doesn't go in, then I can have the second one go in, which means that the third one cannot go in for exactly 1. Or I can have the first one doesn't go in, second one doesn't go in, but then, oh, it likes to do that. But then the last one has to go in, right? So here I have 3 different ways that I can have exactly 1, right? And so here, there are 3 ways to have exactly one shot go in. Okay. Because these probabilities stay the same, it doesn't matter how I calculate, how I multiply down these branches, right? 0.2 times 0.8 times 0.8, because I can only have 1 success and 2 failures. And then there's 3 ways of arranging that, right? So here, if you think about how you would multiply down, you're multiplying the same numbers, just in a different order, right? And so yeah, 0.2 times 0.8 times 0.8, or yeah, 0.8 times 0.2 times 0.8. So really what we have is we have 3 times 0.2 times 0.8 times 0.8, right? And so here, the probability of exactly 1s is 3 times 0.2 times 0.8. And maybe I'll do times 0.8 times 0.8. And then just to have it on again on the next page, paste it here. Just in different orders. Right? But that's what this multiplying by 3 takes care of. Right? So then what this becomes is you have 3 times 0.2 times 0.8 to the power of 2. Which, if we do the calculation, I'll just double check here. 0.8 to the power of 2 times 0.2 times 3 is 0.384. So the cool thing about the binomial is that it's generalized this calculation to any number of trials. Yeah. So the binomial generalizes this calculation to any number of trials. Okay. Which means that we don't need to worry about the tree diagram anymore. Which means we will no longer need the tree diagram. I do think it's nice. Oh yeah, go ahead.
So the tree here represents the number of trials.
So the tree diagram shows us all the possible outcomes. And then depending on the question, in this case, we wanted exactly one. And so then we were able to draw it all out. But now the binomial distribution is going to do that exactly. But imagine drawing the tree for 10 shots, right? And that's perfectly reasonable. You know, I'm in there and I'm trying to get it in. Trying 10 times is not that wild, right? But drawing it out in a tree diagram is insane, right? And so you don't want to do that. But the key part is that all the probabilities, right, have a fixed probability. And so that's why we're able to do this. If the trials were dependent, right, then we can't use this, right? And so that's one of the assumptions that we have. And so in your mind, I want you to remember the tree diagram and how it would look like, right? And then let's say I shoot it 20 times. Also not unreasonable, right? It's not that wild to think that I shoot it 20 times. What's the probability of exactly 4 going in? I want you to imagine. Okay, so you've got 20 layers in your tree, and then you have to find all the branches with exactly 4 going in. Oh, it's a no for me. I don't want to do that, right? But the binomial distribution has made this into a function. Okay? And so the binomial distribution, or the binomial function, I guess.
What if we have a scenario where we say like, so like if you eat the food, like any kind of food, like we have,
Yeah.
you either get energy or not get energy. And then second time you eat the food, you will either get energy or not. But the second time depends on the first because you already got energy in the first trial, you know.
Yeah.
And then the second times,
Yeah.
the probability is same. Either you get energy or not get energy from that particular thing.
Yeah.
How does that look? Is that binomial?
So because the probability is not fixed in that situation, then it's not a binomial distribution. You'd have to go back to the conditional probabilities, right? That probability of A given B, right? And then it's a little bit, yeah. You can only look at, well, I mean, with computers, you can look at as many as you want, right? But by hand, you'll only reasonably look at, you know, 1 or 2 possible trials in that case. Computers can do it all, but for us, we don't want to do it all. But yeah, so good. So that's like one of those examples where the binomial would not apply because they're dependent. Okay, so I guess it splits it across the page. And I don't know if you guys in biology have maybe seen this choose function before. Maybe not. Okay, then I have an example to go through it. So, so the binomial function, okay, In order to be able to deal with any number of trials, we use the binomial distribution to calculate the probability of k successes in n trials, right? So we talked about k equals 1 success, so exactly 1 shot going in 3 trials, right? So now we can talk about 4 successes in 20 trials, for example, right? And so if X is a random binomial process, which means that we have only 2 possible outcomes, and the same probability, right? Fixed probability. For all trials. Right, just to kind of take it back to there. Okay. So how we denote it is X is going to be the number of successes. So in this case, if X equals some general value k successes, then we have this choose function, n choose k. Let me just jot that down here. So it looks a lot like a fraction, but it's not. So this we read as n choose k. And this is what's going to give us that how many branches satisfy that criteria, right? In n trials, how many are exactly k successes? Okay. So before, right, we had 3 trials. Sorry, 1, 2, 3. And what was k? K was 1, right? And so it gets confusing a little bit because it becomes 3, right? There were 3 ways that can happen, but that's the choose function, right? Giving us that 3. So
like if there are like 3 trials, then there will be 3 ways to do that.
That's right.
Is it like always fixed? If we have 4 trials?
No, it's only because it was such a low number of trials. And so, but our calculators do it. So, or there's a formula. I can't remember if I gave the formula in the handout or not, probably not. And I'd have to think, I think it's n, it involves the factorial, n factorial times something. I'd have to look it up. I can't remember off the top of my head. But the key thing here is this is how you find the number of ways that we can get k successes in n trials. So earlier we found that 3 choose 1, right? In a trial with 3 trials, or in an outcome with 3 trials, 1 success was 3, right? 3 branches. Yeah. So this is going to take into account how many different ways can this setup happen, right? And choose k. If we multiply that by p to the power of k, well, p must be the probability of success, right? So the probability of success we're going to denote by p, and in our case, right, p was 0.2, the probability of a shot going in, and k was 1, right? Because I'm interested in exactly 1 shot going in. So then I had 0.2 to the power of 1, right, which is just 0.2. So far it matches what we were doing earlier, and that's the beauty of it. And then 1 minus p is I'll often write it as q, because I think writing 1 minus p is really tedious. And you'll see that we use q quite a bit later on, but you can use 1 minus p if you want. Just know that they're the same. Is the probability of a failure, right? And then we raise that to the number of failures, right? And so here, let me just jot this down here. So I have the probability that x equals k is n choose k times p to the k times 1 minus p to the n minus k. Okay. So this choose function is the number of branches, just to go back to the tree diagram, just so you can kind of start to visualize it a little bit. The number of branches that satisfy the criteria that, or maybe I'll say that have exactly k successes, since that's what we're trying to find the probability of. P is the probability of success to the power of the number of successes. If you think about your branch, right? If the probability of success has to happen exactly k times, well, that's how many times it appears in your multiplication. Right. 1 minus p is the probability of a failure. To the power of the number of failures. Which in n trials, there's going to be k successes and therefore n minus k failures. Right? In 3 trials, we were interested in 1 success, which meant that we have 2 failures, and that's why we had that 0.8 to the power of 2. Right? So it is a scary formula when you first look at it.
So the probability of failure is 0.8 for the first example.
Yeah.
Don't necessarily have to always minus.
No. So usually our brains have already done that subtraction. And so usually I'll write, I'll just write it as Q. Right. So here I would say Q equals 1 minus P, because usually our brains have already done that. So then I'll just call it Q, and Q is the probability of failure. And it makes the formula a little bit easier to look at too. Okay. So once you kind of pick it apart, it's not that bad, but it is a new formula, right? So it's kind of hard to get going with. But, right, let's just look at how the choose function works for just a second. Okay. So we already saw that 3 choose 1 is 3. That's kind of weird and boring, and that can happen, right? Where it's the same as one of the values, but it's not usually the case, right? And so it's just because we only had 3 trials. If we go back to our 3 trials and our tree diagram, maybe let me steal this so I can copy. I don't have to scroll back and forth so much. Oh. Didn't want to do.
So when we write 3, I don't know how to read it. 3 chooses 3. Let me say that.
So let's use this tree to find, and maybe what I'll do is I'm going to remove the, no, I'm going to keep them. Let's use this tree to find 3 choose 0. Oh yeah, thank you, sorry. Thank you. Got so loud all of a sudden.
Yeah.
So let's use this tree to figure out what each of these values are, right? So 3, 2, 0 means that in 3 trials, so I have 3 trials here, so that's why they all start with 3. How many ways can I have 0 successes? 0 successes is going to be, well, nothing here, and then nothing again, and then nothing again. Right? So there's only one way that that can happen. 3, choose 1, we already saw, but let's do it again. Let's do slightly different color, green. 1 happens if I get it in at first, and then I can't get it in any more times. Right. And this we've already seen as 3, but I just want to have them all mapped out. If I don't get the first one in, I could get the second one in, but then I'm not allowed to get the third one in. Or if I get the first, or I miss the first one and I have to miss the second one, then I can get it in on the third one, right? So we see that there's 3 ways. So then, how many ways can I have? Exactly 2. Let's see if I can find a different color here. Okay. So if I get it in on the first one, and then I don't get it in on the second one, then I have to get it in on the third one. Or if I get it in on the first one and the second one, then I can't get it in on the third one. If I don't get it in on the first one, then I kind of have to get it in on the second one as well as the third one, right? Because there's no other branches. So then this is also 3. How about exactly 3? 3 out of 3 ain't bad. There's only one way that can happen exactly. Okay. Good. We can confirm it with our calculator. And I've got the steps on most calculators. I don't know if you're using your phone for calculators or if you have one that you like. Let's see if I have. That's the weird thing about the iPad. I think they don't have, yeah, there's no calculator on here. Or at least like here. It's not weird. Should be like a phone, but it's not. But luckily I have all kinds of calculators on here. Can use the Desmos calculator, which is free, so it's nice. And how do you access the choose function? Well, it's a function, so you have to go to the function menu. And there is the Ncr function. So how you read that is N choose R. Okay. And I think what it wants is in the brackets, you're going to put N, comma, R or K, whichever you want to use. So in our case, let's try 3, 1. And then the answer shows up as 3. Okay. So we can confirm all those, but they're really boring, right? Because there's 1, 3, 3, 1, right? And so that's boring. So what if I wanted to do something like stealing from the handout, 10, choose 2? So then I have to go back to NCR and then main 10, choose 2. And we can just confirm that it equals 45, which it does.
Are they universal?
Pardon?
Are they universal? Are this not like specific?
No, it's universal, yeah. So it's just how many ways can you have exactly K successes in N trials?
Only one.
Uh, No, I'm gonna go,
Yeah, because I think
the choose function should work for any outcome, but then the probabilities would become more elaborate
yeah,
that
because
follow.
I'm thinking of instead of two, we have 5 branches, say.
Mhm.
Then will that function not change? Like, for example, we are saying only one shot. So
It would be,
if we have like something one shot done, not done, and then something in between, it's called.
so it is restricted to 2 possible outcomes because it can only handle the 2.
We are following the tails in all the ways.
Mhm.
They will differ.
Yeah. Do you mean if the probabilities are different? If they
Not
change?
the probabilities, though, but I'll say the trails, the streams.
Yeah.
So, like, not more or less when you say like, I want the probability of exactly one shot,
Okay.
just one shot. So we have like more trails. So, but we have like more streams.
Yes.
One shot.
Yeah.
So it will change the probability. will change.
Well,
Does the choose function change? That's my question.
so the choose function doesn't change, right? But for example, if we added another shot, right, instead of 3, I'm taking 4 shots, right? Then I would have more branches at the end of all these. Then the number of ways that I could have 4 choose 1 is going to change, right? It's no longer 3 ways that I can just choose 1. It does depend on the number of trials, which I think is what you're saying.
But my only question is like if we have 3 branches, if we are adding one more branch, like right from the beginning.
Oh, here,
Yeah,
we can only handle 2,
so is it?
and
only
that's
for
the choose
binomial?
function. Yeah, so the choose function can only handle
Only
2.
for, like binomial.
Yeah, but in theory, it would be able to handle different probabilities, I want to say, but it wouldn't help you very much because then you'd have to write them all out anyways. So then you wouldn't use the choose function, but it would tell you how many ways can this happen, right? And then even if those probabilities aren't the same, right, then you would know how many ways can it happen, right? Okay. Let's see. Okay, so there's a couple of, there's the 100 choose 45 example. And just so you can recognize, so if you go to the choose function and then 100 choose 45. So imagine 100 layers, ding, 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 ding. And how many ways can you have exactly 45? I don't want to do that, right? Right, each stream. How many ways can that happen? In this case, it shows me very clearly that it's scientific notation, but on this calculator, I think it just has like a little space and then 28. Like, so try, like once you have a calculator handy, try the choose function for 100 choose 45, just to see, being able to recognize if you have scientific notation, if it's not clear. Because if you do, so there's a choose function here, and I think I do 100 choose 45. Oh, this is not the one I was thinking of. Sometimes there's just like a little space. So let me just screenshot this. Oh, not this one actually.
Does the
Delete.
calculator works the same like in brackets? Yeah,
It kind of depends on the calculator, like, so for this one, there's a second function, a choose function. I'll let you have this one. The choose function is here. So then I would do 100 and then hit second this one and then 45 enter. So it
you're like
depends on,
the number first and then.
yeah, but you can kind of play around with it. You can think that one for a sec if you want. So you kind of have to get to know your calculator a little bit. So here. Crop this. So kind of, yeah, play around with your calculator, whichever one you plan on using, right? It's all our quizzes and stuff are going to be open books, so you can kind of use your phone. I don't like using my phone calculator. I find that it's very difficult. Pardon?
Is it allowed in exam?
No. I'm like, officially no. But I don't really care, because I mean, if you know how to use your calculator and you prefer your phone, I just really don't like using my phone calculator, because I find that it's a really bad calculator. Like,
iPhones have really bad calculators.
yeah, and I just find it very frustrating. So I don't like to use it.
Sometimes even simple calculation gets messed up.
Mhm. Yeah.
When you're sending-
Yeah. But then, so the Desmos calculator, because I think we've used the Desmos graphing calculator. And then there's a Desmos, so this is from the Desmos calculator. Is free download.
It doesn't have the choose function.
Yeah, so I think then you would have to no, so it has the factorial, which is the exclamation mark. So then you would have to use the formula. And I feel like I can't remember what the formula is off the top of my head. I'll look it up, but do you remember x factorial is x times x minus 1 times x minus 2 all the way down to 2 and then 1. So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And the choose function, n choose k, and let me, is n factorial. I have to look it up, can't remember. Cannot remember.
N factorial upon n minus k factorial.
Like this.
Yeah, n minus k.
Nice. Which means that if you wanted to do 10 choose 2, for example, right? And this is kind of getting off topic, but it's good to know these things because they do come up. So then, for example, if you want to do 10 choose 2, that's going to be 10 factorial divided by 10 minus 2 factorial times 2 factorial. There's a trick though for these kind of basic ones. Let me just scoot it down here. If you write this out, this is 10 times 9 times 8 factorial. There's a reason I stopped there, right? So you can kind of stop at any point, because then I have 8 factorial that I can cancel, right? So that's the sneaky trick, 2 times 1, which is just 2, right? So then I'm able to cancel this here, dink, dink. And now I just have 10 times 9 divided by 2 times 1. It's not always that breezy, but that's just the trick that you would use. Yeah, so I'd way rather use my calculator. 10 times 9 is 90, divided by 2 is 45, which is the same as what we found here, right? We did 10 choose 2 already, which is 45. So kind of 2 ways that you can do the same thing. Okay. So in the handout, there's a typo, probably still. Yeah, there is. Should be 3 choose 1. I don't know why it says 3 choose 3, but it's 3 choose 1. Typo galore here. Okay. Oops. So we can confirm our calculations that we just did in the, or not just, that we did in the tree diagram, right? And we kind of did a really thorough mapping back and forth. So it's supposed to be 3 choose 1, typo, and then 0.2 to the power of 1, and then 0.8 to the power of 2, right? And that's how we get the same formula, right? It's not surprisingly the same results as we found using the tree diagram. Okay, so this is where it gets a little bit more confusing. And let me see where I want to go to. Okay, great. Even though we have kind of these categorical outcomes, right? Yes, no, successes, failures. We can still find the mean, which we call the expected value typically. So we can still find the mean and the standard deviation of a binomial distribution with n trials and p, the probability of success. So BNP is shorthand for a binomial distribution and for a binomial with n trials and p probability of success. We say that those are the 2 things that we need in order to describe the whole binomial distribution, right? And so here we see that n, oops, and p are the only things we need to describe a binomial. Right? How it behaves. And then we can specify the probability of k successes, right? But in order to know what that binomial behaves like, we only need to know n and p. we can think back to the normal distribution, right? In order to calculate a probability associated with a normal distribution, we only need the mean and the standard deviation, right? And here we're going to come full circle, but it'll have to wait until next day because there's no way we're getting through a huge example before then. But so N and P are the only things that we need in order to describe a whole, a binomial distribution. And so the mean is the expected number of X, the expected number of successes. So here, this is E of X, which is the expected number of successes in N trials. And our brains already do this for us. If I say, oh, I'm going to try to get this shot in, I'm going to try 10 times. How many times would I expect to get it in the hoop if the probability is 0.2? I would expect to have 2 of those, right? 20% of those 10 go in. And what did our brains do? We did 10 times 0.2, right? And so our brains already understand this idea of, okay, if there's some probability of success and I try so many times, I expect N times P successes in that number of trials. The standard deviation, not so much. Our brains don't automatically know how to do that, right? But here I'm telling you that it's the square root of N times P times Q. And then sometimes I'm nice and I have a little footnote here saying where Q is 1 minus P, right? And so here, just kind of connect those two, right? But just to make it look a little bit nicer, I just use Q. So the standard deviation is the spread, right, of how many successes I'm expecting, right? So I expect this many, but then there's some spread, right? So a little bit weird, but what we'll see next day is that we're actually going to be able to approximate the binomial with the normal distribution. So then the binomial, as soon as we have a large number of trials, and I mean like 100, 200 trials, then we're going to be able to shift it to a normal distribution and just use the mean and the standard deviation as part of our normal distribution.
I'm just thinking how to do some like example for a bigger picture when we'll be like doing all the things we have for normal, conditional, and triangle.
Mm-hmm.
So how we differentiate binomial? Is it just like, okay, so we have to write outcomes, let's stick to binomial?
Yeah, exactly. So especially if there's 2 possible outcomes, a lot of questions will say, is this a binomial scenario, right? Just to kind of nudge you in the right direction. So I like to keep those in there where it's like, do you think this might be a binomial? Why or why not? Right? And then your argument would be yes, because there's only 2 possible outcomes and with a fixed probability.
Yeah, because I was thinking of bigger picture, like an example. So what it is.
Mm-hmm. So the hardest one to differentiate would be like the conditional probability, teasing that away from the binomial. But a conditional probability is going to have a probability that changes depending on what happened previously.
Yeah.
And so I'm only going to make you look at, 2 possible, 2 trials in those cases. But we didn't get to the example today, but we'll pick up with the example and the normal approximation next day. You can try it on your own. Yeah, it seems weird to read an example for 2 minutes, so we'll stop there. But
Question. It's not like thought it's like stats.
Oh, sure. I'll stop this recording